series of lectures on plate tectonics. And in the last lecture, which is also on this YouTube channel, we devoted introducing Alfred Wegener and his hypotheses on plate tectonics. Now we're going to talk about some of the evidence that was compiled by others to build up to the theory of plate tectonics, to lay a lot of the foundational groundwork. So Alfred Wegener talked about continental drift. That was his hypothesis. And eventually that was validated and improved by others, including Marie Tharp and Bruce Heezen. They compiled bathymetry data from military and other oceanic surveys and made a set of beautiful maps right around when the science was just starting to come to a point where geologists could agree on this idea of plate tectonics. So here is the Tharp map, a beautiful representation of the ocean floor, especially across the Atlantic. And you see this amazing mountain range that goes right down the middle of the ocean, and with a series of what look like little indentations on the side, and then one indentation running right down the middle. It almost looks like stitching on a baseball. But just think about the scale of this mountain range. It's enormous, right? It travels all the way down through Iceland, all the way down the middle of the ocean. You know, it's longer than North America and South America combined, right? And eventually, with the help of Harry Hess, we come to realize that these mountain ranges represented plate creation zones, where you're generating new oceanic floor along these mountain ranges. And it's like a conveyor belt of new ocean plate. And here is Harry Hess himself working on drilling rigs like the Cuss 1. And he is the one who hypothesized about this idea of seafloor spreading, where these mountain ranges do represent the plate generation areas, right? And this topic, this whole idea of continental drift, continents moving around, and seafloor spreading is heavily debated all the way up into the 1960s. A number of interesting papers came out in the late 60s, including one by John Oliver, but many other contributors to this field, keep in mind, right? And you get these amazing patterns showing up in earthquake record, right? So one of the issues with seafloor spreading, if you think about it, is that if you're constantly generating new ocean plate, wouldn't that mean that the crust of our planet should be getting bigger over time, and there would essentially be an empty volume inside of our planet? So there had to be some mechanism to take care of the old plate, to eliminate that extra surface area that you're creating at these divergent boundaries, which you'll learn that they'll be called, right? And if you look at IRIS's amazing webpage, you can take a close look at patterns of earthquakes that we've been measuring, and we have the ability to figure out exactly where these earthquakes are happening. And if you notice something, this purple area is near the surface of our planet, and you go from blue to green to yellow as you go deeper, and you can see that earthquakes are essentially outlining what we later understood to be what's known as subducting plates, or pieces of oceanic crust diving down into our planet along deep ocean trenches, right? So that's kind of what we started to figure out, and we get these things called Benioff zones, which delineate the subducting ocean plate. So it kind of supports and provides an explanation to where all of that extra plate is going after we create new plate. Just a quick refresher for those of you unaware, there's two major types of crust on our planet, right? And that would be continental and oceanic. Continental, you could say, is generally comprised of granite, which is a felsic igneous rock. We'll talk about those more in later episodes. But all you have to know is that it's thick, like a blanket that keeps heat in. It's always low density, more squishy, than oceanic lithosphere. And like I said, it's a felsic type rock. That describes its composition, the chemistry that it's made of. Then ocean lithosphere is generally thinner and denser, not as good at retaining heat, and it gets even denser as it cools off and ages. And it's mafic in its composition. This is a map showing how thick different parts of the plates are, the different parts of the crust are. And you can see that the continents are generally much thicker. And these units are in kilometers. And that the oceanic plates, the oceanic crust, is generally thinner. And then here's a USGS figure showing just the different layers of the planet, just so you can help visualize what's going on with this plate tectonics theory. And those are our different layers. And I won't get into this in great detail here, but just be aware that our planet is broken up into these different layers, including a solid inner core, liquid outer core, mantle, and then the lithosphere. So that's kind of a quick overview on some of the foundational stuff, and we'll get into more detail on additional piece of evidence in the next lecture. And that concludes this lecture here.